All right, let's see what you guys said first. All right, most of you said C to the left. That was also true for the morning lecture. What's the right answer? Well, if we go back and think about it on the previous slide, get this out of the way. If it's coming out of the board at you, you grab the current. If you grab this current, your fingers are going to be going up at this point, grabbing it, right? In other words, the field lines do that. They go around in this direction. So at this point, they point up. So the magnet will point, or the compass will point up at that point too. If you move the compass up here, it would point to the left. Over here would point down. Over here would point to the right. So it follows the direction of the magnetic field lines. So the correct answer is up, A, which, well, a quarter of you got it. I'm still puzzled as to why students go for the left. Who chose left, and can they explain why? Yeah, go ahead.
I was thinking of sort of like the direction at the tip of the north arrow, and I was thinking of that as the left.
Yeah, you don't put your hand on at the compass. You put your hand around the...
I was thinking that I put my hand where the current is, and then I imagine a circle coming out, going sort of to the, it would be at the left, sort of right above the current, and then at the edge of the compass, the top edge of the compass, I think it would be pointing to the left.
Maybe it would be less confusing if this were a smaller graphic? Maybe. Or further away or something?
I mean, I think I just got it wrong.
Okay. Happens. I mean, it hadn't had much time to absorb and synthesize this in your memory, so... Well, you'll have DL to go through it. You actually, I think, do this in DL. But okay. Now, if we take a bunch of wires and arrange them in certain ways, we can make lots of different shapes for magnetic fields. And we have a bunch right here. Imagine you take a wire and you make it, bend it into a loop so that the current flows around in a circle like that. We can arrange that, right? It's not so hard. In that case, imagine what happens if you do the right-hand rule again. You grab the wire, basically, with your thumb pointing in the direction of the current. Then your fingers, generally speaking, point in the fields near the wires are circles, but as you get further away toward the middle, they all add up to one big uniform field pointing in the up direction there. Now, this picture here is slightly inaccurate, but it gives you an idea that when you're close to the wire, it's still a circle, like it is in the previous slide and exercise. And then the field lines sort of open up because you're adding up the upward going ones from here to the upward going ones from here. And in the middle, they add to a nice straight field pointing in one direction like that. So that, another way to visualize it might look like this. If this were the current right here, you get this dipole-looking field like so around a loop of current. You always have to remember when you see these diagrams that we're just looking at a two-dimensional slice through what's actually a three-dimensional field. So you kind of have to use your imagination and think, what does this really look like in all three dimensions? So if I had a coil like this, and we put a current through it, there's lots of windings here, so you can get quite a lot of current going. The magnetic field is up and in all directions coming out like so. So that's how you should visualize it. It's really difficult, of course, to draw that on a two-dimensional screen. Now, the more loops you have, the more net current you have going around in the loop, and the stronger the magnetic field is going to be. So that's why when we have a magnet loop like this, there are many windings. I think there's perhaps 100 actual windings of the copper wire in each of those two loops. So yes, we've arranged two loops, let's say, like this. We call these Helmholtz coils, as you'll see in a minute. And now I'd like you to think about something else. What about the force between those two loops? You could either do this by thinking of them as magnets, two magnets, because they each create their own magnetic field, the two loops, and imagine what two magnets might do. Or you could think of it in terms of the force on a moving charge, which we learned about in our definition of the magnetic field with the first right-hand rule. So here we go. We have two current loops near each other, aligned axially, meaning there's an axis of symmetry and they're both aligned with that axis, as shown. Now, do the two loops attract? A, because their magnetic fields are aligned. B, do they exert no force on each other? Or C, repel because their magnetic fields are aligned? So go ahead and discuss with each other.